Okay, why does mutation work? Robert Geist came to me. So this is a guy I worked with who, a long time ago, my first academic job, who said, mutation is nonsense. I said, well, why did you guys hire me? So he told me this 3 weeks into my job as a 28-year-old, beginning 27-year-old assistant professor. I said, Professor Geist, you should call me Buzz. Professor Buzz, why did you hire me if you don't think my research has any relevance? He said, well, I thought there might be potential, but some people didn't want to. That was too much honesty. Like I asked, how do I look on camera? And he said, do you want honest answer? No. So finally, I forced him to play with the mutation system. And he came back and he said, it does work, I get it. And this is what he said, that if there's a problem, there's usually, not always, there's no absolute here, there's usually a mutant or a set of mutants that you can't kill except with a test that also finds the fault. So that's why it works. So I turned that into a challenge I give students sometimes in classes. Find a fault in a program, generate all the mutants of that program, find a set of tests that kill all the mutants but that don't find that fault. I've given that challenge, I don't even call it a homework assignment, to somewhere around 100, 150 students. Only 2 have been able to solve it. It's actually very hard to do. To find a fault that your mutation adequate test sets will not detect. It's possible, but it actually is really hard. So that's Buzz Geist's fundamental premise. It's not absolute. What's really going on is the mutants are steering you towards a really good set of tests. That's what's really happening. Oh yeah, there's my challenge problem. So it depends on the operator. So how do we design mutation operators? Well, at the method level, so the examples I gave earlier, we can say they're at the method level because they modify individual statements. Every language has, its own unique features, but they all have variables and they all have operators. So a lot of the mutation operators are very similar. So if you look at the mutation operators for C, they look a lot like mutation operators for Java, but then there's some differences. As we said, they do one of 2 things. What usually happens is I have a new language, so I want to design a mutation for Ada. No, PL1. Does anybody know PL1? See, that's an ancient language. Nobody under 50 is going to ever hear of PL1. Be glad. It's a mix of COBOL and Fortran. That may not make sense. Now I'm talking about classic rock, right? Does anybody know Pink Floyd? Oh, I'm glad your education hasn't been totally useless, some of it. If you don't, I don't know, you should. Where was I? So I want to design operators for PL1. I design a whole bunch of operators to change everything I can think of. Then I ask which of these are useful, which are not. And that's actually a pretty difficult process. So we want effective mutation operators. So they give you mutants that are, generally speaking, hard to kill but not impossible to kill. That is, we don't want equivalent mutants, but we don't want the trivial mutants. And hard to kill essentially means a small part of the input space will kill the mutant. Okay, that's really what we want. And this is quite likely. It turns out there's a lot of overlap among mutants. So we often get 1,000 mutants for a relatively small program, but we'll need 25 tests to kill all 1,000 mutants. That means there's a lot of overlap. That's a big part of the expense, and that's a big part of the current research, is reducing that overlap. So here are the Java statement level or method level operators that are used in a tool, Mujava. I had an idea of having you all download Mujava, install it, and use it, but in my classes I found it takes people 15 minutes to sometimes 4 hours to get Mujava up and running on their computer, so I gave up because I didn't want to use the entire rest of the day. Actually, I did, but your afternoon speaker sent in a note of complaint since he wasn't going to be able to do anything except go to the beach. I don't know why he's complaining. So these are some of the typical things we change. I'm not going to go through all of these. They're pretty simple. But I do want to do now a more active exercise. You'll need a computer and you'll need a partner. And internet. I really love eduroam. It's my favorite. Everywhere I go in Europe, my phone connects automatically, and you can usually get this guy. So Code Defenders is a game that Gordon Fraser and Jose Miguel Rojas at Sheffield invented, and this was published in March, I think, at the ICST conference, and I used it in class, and it was a lot of fun. So I want you to play Mujava, or play Code Defenders. So you start the Java class under test. You have an attacker who creates a mutant, and a defender who creates tests. So what I want you to do is to open up your computers, go to this website. We'll spend about 10 minutes. You're not going to get very far, but this evening you have more time. You can play some more if you like. It turns Mutation into a pretty fun game. So find a partner. So this is a 2-player game. If you don't have a computer, you want to make it a 3-player game, that's fine as well. If all you have is this, you would be at a severe disadvantage, but it is actually possible, I understand. We have, the attacker is going to create a game, and I suggest you have several programs up there. We use CalJava in my testing class this spring. Change the level to easy. Remember your game number. Then the defender uses that number to join your game. And at the end, we're asked to complete a survey. I don't know whether they protect these passwords. So I would recommend not using a password, not the same password you use for your bank account, for example. For all I know, it winds up public. So here's the first screen you should see if you get the Code Defender. How many people have gotten there? Okay. If the attacker creates an equivalent mutant, the attacker loses. But I think the way they said it is that the defender has to claim this is equivalent, and the attacker tries to prove that it's not by creating a test to kill it. And if the attacker can't kill it, then the attacker has to admit, yes, it's equivalent, I lose. I think that's the way the game is set. So you don't want to create equivalent mutants. Let's go on then. So the next question is about mutating input space grammar. So slightly less than half of you said you've seen introduction or you've read a paper about mutation. You're unlikely, I think, to have seen this because it's less common. People haven't thought about this for a long time, but I think it's a potentially really valuable practical use of mutation. So I'm going to start with just a little background about what we mean by the input space or an input space grammar. So the input space is all the possible inputs. So a Java compiler, all Java programs, that's in the input space to a Java compiler. But actually Java compiler tells you if you have a syntax error. So almost Java programs are also valid input space. In fact, if you give any random string to a Java compiler, it will come back and give you syntax errors. So really all possible strings defines the input space to a Java compiler. So it's a very large input space, in other words. We always have an input space. Some of them are much bigger than others. Some are harder to define than others. But we can always describe that input space, and we need to for the users to use it. So it's usually informal, sometimes incomplete, user manuals, even the method signature at the method level. You may have the Java language, for example, but any type of user manual. Have you ever seen on the internet something like, well, it's usually called something like hacks you didn't know existed for using your iPhone? Has anybody ever seen things like that? They're telling you things about the input space to your mobile device that a lot of people don't know about. Right? So we don't know the complete input space to this thing. But so they're telling you things. If you use, how many people have used Excel? Have you used all of Excel? No, I don't think so. Nobody has. So nobody knows all of Excel. How many people use VI? If you don't, you should. It's a much better editor than whatever you're using. How many people know all the VI commands? That's a trick question. No, there are VI commands that are never documented. So it's a very large input space. I've been using VI since 1983, long time ago. I don't know all the commands, and I use it heavily. I've written hundreds of thousands of lines of programs with VI, but I don't know all the commands. We can usually describe input spaces as grammars. We don't often do that, but we usually can. Probably we always can, but sometimes maybe it gets really complicated. We usually don't have the grammars, but here's a very important principle as a tester. If you have some software artifact that you're trying to test or develop tests for, if you're doing model-based testing, if you're trying to develop tests based on model and the model doesn't exist, or the graph doesn't exist, or the grammar doesn't exist, by creating that model or that grammar, you're going to find a lot of problems. Because what you're really doing is you're creating the specification to the software in a different form that may have been written down before. And you'll find problems. You'll find things that aren't inconsistencies or things that are incomplete about it. So this is, as a tester, this is always valuable. And you always go back and say, well, I'm just trying to describe the input space of the program. So you go to the designer and say, does this look right? And the designer will always say, yeah, I don't know. We didn't think about this. So you will find problems right away. But then you can use it to develop tests. How many of you how many people have heard the term input validation? Okay, good. And I can start at the beginning. It's pretty simple. It's input validation means you're asking, here's some inputs. Can I process this? Is this a valid input? So you have a precondition. So month should be less than or equal to 12. That's a precondition. So input validation might check the month and ask if it's less than or equal to 12. For that matter, it should be greater than 0. Although I'm not sure if that was written down. So is it in the appropriate range? So that's an input validation step. It's a very important part of initial checking of software. So if the data is invalid, the software should do something. I mean, sometimes it says, no, we don't accept that. Go try again. Sometimes it changes it. Maybe if it gets to month 14, it changes it to 12. Who knows, or something, or maybe it returns and says, it's giving the difference between two dates, right? A valid response may be, I can't give a distance between these dates because the second date is invalid. I don't know. But a lot of programs don't do it well. In fact, a lot of programs assume all the input data is correct. If you've studied database, they talk about database integrity. You may have heard that term. That's essentially the same thing. Is the data, or all the data in the database, valid? If yes, then you have satisfied database integrity. This is very important in another realm that's much more important than it used to be. Remember the other conference we mentioned at the beginning? The security people? Vast majority of attack vectors are through invalid inputs. Okay, so this is crucially important to software testing now, much more than it used to be. And then we changed. Has anybody heard of the Ariane 5 disaster where we blew up a rocket? Yeah. The software worked in the Ariane 4. Then they put it in a different context. And it got input data that they never got in Ariane 4, and it blew up the rocket. What was it? I think an exception was raised and was not handled. So that's a classy. But this happens all the time. We take software, it works here, we take a chunk of it and we put it somewhere else and it doesn't work anymore. It was never actually correct. Oh, there's that word again. It had the problem in the old version, we just never got to that problem. It was not reachable, perhaps. So input validation is essentially a form of testing where we're finding what happens when I get invalid data. And maybe what happens is okay, maybe not. But what should happen is essentially a policy decision about the specifications. So how do we represent input domains? It turns out to be very complicated. I think of this in terms of three different types of representations. We have and I'm going to give a couple of examples. So this is, remember I said I was a math major? I always liked Venn diagrams. This describes the set of desired inputs. So I call it the goal domains. Notice it's kind of irregular shape. There are little corners here and there because a lot of input domains are. It's not usually very regular. Here's the way we describe it. Notice it's close, the specified domain, but it's usually not exactly right. And actually stop sign is very simple. What's the goal domain for a stop sign on a road? We have a resource that we're sharing, the intersection. It's that we share the resource safely and fairly. Everybody gets the chance, we take turns, and it's safe. So if you come to an intersection, there are no trees, there are no obstructions, it's 3 in the morning and it's dark, okay. It's not actually dark here at 3 in the morning in June, but whatever. Assume we're somewhere where it is dark at 3 in the morning. Headlights, you can see 4 kilometers in every direction. You don't need to stop. You can just slow down enough to make sure you see and then you continue. Other times you need to stop. So the goal domain is actually pretty complicated. Depends on the conditions, the time, etc. The specified domain is usually that you have to come to a complete stop. That's the way we learn in driving school, correct? But then we have the implementation domain. What's acceptable by the software. Now with the stop sign, the specified domain is pretty simple. The implementation domain is quite different. It depends, is there a police officer? Can the police officer see you? Now if you come slow down to what's obviously a safe speed and there's nobody there and then you continue, will you get a ticket? Depends on the police officer, right? Is a police officer feeling energetic? I don't know about Europe and the US, you're much more likely to get a ticket on, say, 29 July than on 2 July. Why? Because a lot of cops have quotas. They have to give out a certain number of traffic tickets per month, and if they're short on the quota, they'll stop everybody. If they fill their quota by the end of the month, then you can get it, but you never know. So that implementation domain is actually quite irregular. With software, it's usually the implementation domain tends to be the simplest. Here's another example with the credit card. My neighbor had this problem a month ago, couldn't use a credit card to buy a ticket. The software wouldn't let him. So a credit card number looks sort of like this. So I got this from this website. This is just a summary. The first digit is a major industry identifier. So is it a bank or a travel agent or whatever. 6 digits in the length specify who gave it. So Visa, I think, is 12. American Express is 15. Other kinds of credit cards have different lengths. The final digit is check. So they add up all the numbers, or there's some formula with all the other numbers, and they compute it to 1 digit, and that's the check digit. Maybe it's just the remainder. The other digits identify your count. So that's the goal domain. The specified domain is first digit is 3, 4, 5, or 6. So my neighbor had a U.S. government issued credit card. He was traveling on the U.S. government's dime, and he couldn't buy a train ticket in Germany or France, one of those. I think it was Germany. Why? Because I think it was a 7. I think that's the U.S. government issued. And his point was, this is a NATO country. I'm traveling on NATO business, but I can't buy a train ticket. He had to use his personal credit card. The length, so this is, I think that's American Express and that's Visa. But there are actually credit cards that are shorter and longer. That's just by far the most common. What do most programmers do? That's a rule, that smooth circle. Are all the digits numeric? That's what programmers use. So this is real. This is what the specifiers say. This is what the programmers do. Very common. So back to that picture. What that really means is that this region around this that encompasses both, that's a rich source of errors. That's a place we really want to test, right? This is an unhappy path test. My Visa card that I carry around all the time, it's in the middle. That's a happy path test out here. Now, this happened to me. I was trying to buy a train ticket in Sweden a few years ago, and I wanted to have the train ticket sent to here. Software wouldn't let me. You know why? Because I have the wrong number of digits on my phone. It wouldn't recognize a US carrier phone number. It's 10 digits plus the country code. And it essentially said, no, you have too many digits in your phone number. So it refused to give me my ticket on my phone. And I didn't have access to a printer, so I finally had it sent to my friend's phone. So we're traveling together. He scanned 2 tickets. And the ticket agency on the train said, why doesn't he have his own ticket? He said, he doesn't have a phone. And the ticket agent frowned. He said, he's American. So, oh, okay. They don't have phones. And in fact, I mean, based on Swedish railway system, I don't have a phone. It's not a valid phone. So that's a rich source of errors. I mean, clearly Swedish rails would like to sell me a ticket because I was going to pay for it. But their software was broken. This happens all the time. And again, by the way, this is also a rich source of security vulnerabilities to lots of particularly web-based software systems, but software in general. So how do we do that with tests? Well, the grammars let us focus on those interactions. The original work on this was based on web services, which use XML, which has a very strict structure. So we used a formal model of the grammar. This is a paper I had, I guess it was about 10 years ago now, with BNF, and we use XML and schemas. We're able to create valid tests and invalid tests using mutation. So we mutated the grammar to develop usually to develop the invalid tests, right? Remember with the test, you don't just want valid tests, you want invalid tests as well. So here's an example. This actually comes from some consulting I was doing a few years ago. This is very simplified, but this is a grammar for a program that processes deposits and debits. How many people are familiar with BNF, Backus and Hour form? Okay. I mean, if you're not, we start with bank, replace it with an action. The star means 0 or more. An action can be either a dep or a deb. A dep is the string deposit followed by an account and amount. A deb is debit followed by an account. An amount, I really simplified this, 4 numeric digits. A $sign, okay, so this is US Bank. At least 1 digit, possibly more, followed by 2 decimal digits. So those are the decimal digits. So this is a grammar that defines the input space. Again, this is not the real banks. We're making certain simplifications. This allows actually an unlimited amount of money. Most banks have a limit, how much money you can deposit, particularly online. So here are a couple of possible tests. Deposit into this account this much money. Debit means remove, if you're not familiar with bank terms. I think that's Latin, actually. So how do we use that how do we use mutation for this? Well, we can replace the non-terminal, so account replaced with amount, the amount replaced with a digit. So this is the original statement in the BNF. These are the 2 mutated statements, so that can yield a couple of tests like this. And these are pretty good tests. What happens when we do that? Here, terminal symbol replacement, replace the $sign with the dot. Yeah, the dot with the $sign here, the dot with a vertical bar. So we might get, wait a minute. Oh, I think that's a 1. In this font, I can't tell the difference between a vertical bar, an L, and a 1. I think that's a 1. And then we can delete terminal and non-terminal symbols. So we delete the deposit here. In this, we delete the account, delete the amount. So we might get these tests. So these are all, I think these are all invalid tests, right? Can be created by applying simple mutation operators. Now it turns out that in that little consulting job, this test, or a more fleshed out version of this test, found a fault in the software. It applied this deposit to the last account that had been activated. So it kept that value in the memory. It interpreted this correctly as an amount because of the initial $, I guess, and then it put that in somebody else's account. This was really funny. In the meeting, the developer was really upset. Eventually, was almost yelling. That's not a fair test. Nobody would ever do that. You can't do that at the ATM, the bank machine. You can't do that anyway. Nobody, blah, 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 blah. The manager said, but why did it accept it? Well, because nobody could ever do that. And he said, so next year we're going to put this online so people can take pictures of their phones and then type in the information. What's going to happen then? He said, it's not a fair test. He was so, at first I was sort of taken aback, and then I realized the manager understood what was going on, and then I was trying not to laugh, actually. I felt sorry for the developer because he just took it very personally, and he was angry at me for finding the problem. But the manager actually had it straight, and I assume they fixed the software. Now I deposit money by taking pictures with my phone and sending it, and I always think about that and thinking, I hope they've got my account number correct. At least when I deposit. If I debit, I go withdraw money, I'm happy if they use your account. That's fine. Or somebody with more money, not students. I don't want to steal from students. Alex Petrenko's money, that's fine. He's got lots. So this is how we use mutation to generate tests. How many people know XML? Good. If you don't know XML, you should. It's ubiquitous, and it's incredibly valuable, and also pretty simple. So it's not like telling you should know C++, which is really hard and painful. XML is really easy and useful. So here's a book XML message. So these are the tags. This is the content in blue. XML messages are defined by grammars. Primarily a schema defines what this looks like. So they can define types and facets, and that defines the input space. So here's a schema for that book grammar. You can ignore most of this if you're not familiar. It doesn't work for well, the white. So max occurs means we can have as many books as we want. There's not a minimum, so we can have 0 or an infinite number. We have string, ISBN type. So string is built in. Price type, year type, and ISBN type are defined somewhere else. So a price type, it starts as a decimal, but with a restriction 2 digits after the decimal and a maximum value of 1,000. So you can't have a book that costs more than 1,000. Actually, that doesn't say the units. So I guess this is unitless. But that could also, that should be actually part of the schema, shouldn't it? Which unit? So that's a grammar, and that defines the input space to whatever program is processing, this XML message. So we can use that to define tests. We can mutate those. If there's no schema, create one. You'll find mistakes, always. If software is using XML and they don't define schemas, they have problems, guaranteed. So create the schema. If they're not validating, they should. So you can validate against the schema, and that solves all sorts of problems. They're less likely to check the facets. So those are the important things. So you can do things like change the number of digits to 3 and 1, change the maximum inclusive value to 100 to 2,000. So if there's an XML, we can change 505. We can create another test that changes 37.5 to just 1 digit. So is that going to be accepted? Is it going to be 50 or 0.50, or is it going to be 0.05, or is it going to be rejected? I don't know, but that's what we want to find out. The max include, so we change to just under this max inclusive value. Probably won't find the problem, but if we change to 1,500, what's going to happen? What's the software going to do? I don't even know what correct behavior should be, frankly. But those are the kinds of things this testing allows us to find out. So this is actually kind of a fun, this is a homework example, a homework exercise I use in class. And they have fun with this. So this is just a little servlet I wrote for another class. It does something simple, calculating numbers. And there are a couple of, there's I think 3 different faults that are in there intentionally, maybe a couple that aren't intentional, that require you to actually do really good testing to find. Okay, let's talk about research in mutation. In preparation for this, this is not complete. This is a little short. I decided to go back and just look what's been published in the past 3 years. So 2014, 15, 16. There's a workshop every year associated with the International Conference on Software Testing, Validation, and Verification that is usually at that conference. It has been for the past several years. So there are 34 papers in that 3-year span. At this workshop, there are only 5. This was surprising. So this is the biggest conference in software testing, International Conference Software Testing, Verification, and Validation. Every year, next year it's in Tokyo. Year after that, I think it's in Sweden. Oh, what's the name of the town? Mälardalen, yes. Västerås, yes, Västerås. Everybody should go there. ICSE, International Conference of Software Engineering, is, you know, the big granddaddy conference in software engineering. ISTA is the National Symposium on Software Testing and Analysis, kind of focuses more on analysis. It's a lot smaller, more restrictive. It tends to draw a lot more from North America than Europe. Then I looked at some journals. So the major testing journal focuses on testing, software testing, verification, and reliability, published by Wiley. Then 8 mutation papers, transactions on software engineering, of course you all know that. Published 3, empirical software engineering, which is one of the best journals, although in software engineering, although the editor complained to me that since STVR has been stronger lately, they've gotten fewer testing papers. Now I looked at TOSM, ACM Transaction Software Engineering Methodology. I couldn't find any mutation papers in the past 5 years, actually. So this is not complete. There are lots of other conferences and workshops. I just looked at these. So these are the number of papers since 2014 published in those. And also for these, I looked ahead for the upcoming issues as released on the website. So it's not just the issues through June 2016, but for 2 or 3 issues ahead. So that was my sample. Again, it's not complete. And I looked at title. So there are probably other papers that use mutation in one sense or another. And I divided them up by topic. So I wound up with 10. So the most have been applying mutation to new languages or to new applications. And I'm going to go into detail on that one in particular, because that was close to half, I guess, of all the papers. There have been 8 papers which surprised me, which are on the subject of reducing the cost of mutation by having fewer mutation operators. So I generally called that minimal mutation. Not all of them actually use that term. And I'm going to talk about several of these. One of the big problems with mutation is we get all these equivalent mutants. We get too many. It's a big cost. And it's a negative cost. And that as a tester, your goal is to try to show that I can't kill this mutant. You don't improve your testing because you don't get a test from finding equivalent mutants. So particularly a practical tester finds equivalent mutants very, very disruptive because they cause work, but they don't yield any benefit. Are you all familiar with the term return on investment? It comes out of economic theory. I put work in and I get something out, right? I pay for a meal, I get some value for the meal. The return on investment for detecting equivalent mutants is negative. So that's really, really frustrating. We always want positive ROI, not negative ROI. So that's one of the biggest problems. So I found 4 papers. I mentioned automatic program repair, which is really automated debugging. So we have a bunch of tests. We have some tests that fail. So we know there's a problem with the software. So automatic program repair tries to fix the program automatically so that those tests succeed. Now the ones that cheat can change the tests, like the Oracle. That's not good automatic program. So the next group was automatic test data generation papers, and that's the biggest part of the work in practical testing is finding the actual values. So if we can do that automatically, that's a big savings. How to do the process, how it's applied. So these are kind of general there. There have been several papers on tools, including the Code Defenders tool that you just used. That was one of those. Whether mutation is valid in experimental settings. So one of the primary goal or uses of mutation in the research community is to evaluate another testing criteria. So I have a cool way to generate tests, and I want to know how good are these tests. Well, one of the ways people often do is they measure how many mutants does a set of tests kill. Okay, so that's a very common use of mutation in the research literature, not in practice. I don't think I found papers that use mutation in this way because the mutation wouldn't have shown up in the title of the abstract. I just did a keyword search in those papers. So probably a lot more papers that use it in that way. So I just found one about that process that essentially said we did an analysis that found that this is a valid use of mutation. That is, mutation is a valid proxy for actual faults. Okay, so that's a common use. There's an idea called higher order mutation. Can't remember if I have something specific on that. If I don't, I'll come back to that. Mutation is, we usually create each mutant as one change. A higher order mutant, we make 2 or more changes. So it's higher orders of changes. And then there are some others that I didn't even understand well enough to categorize. One, by the way, I had reviewed the paper. I didn't understand it when I reviewed it. I didn't understand the final version, and I still don't understand it, but it did get published. I was not in favor of the publication because I couldn't understand it. But I don't know how to categorize that. And the others, I just didn't come to me. So these are the language applications. I found 24. So on the left, these are papers that defined how to use mutation to test database queries, mutation operators, say, for Simulink, mutation operators for aspect-oriented programming. WSBPL is a web services language. JavaScript, I'm surprised there's only one because that's a huge source of problems in web applications is bad JavaScript. I read a stat recently that said that JavaScript is the most widely used language at the moment, which is scary because it's a horrible language. Plus, it's really easy to get it wrong, and so we don't test it very well. Python mutating Haskell, which is that an AI used language? I don't know Haskell. I just know that one of our AI guys talks about it. He does AI and robotics, so I kind of guess does anybody know Haskell? Oh, is that AI robotics? What is it? It's for? It's functional. Oh, I know the AI folks love functional programming languages. And then that's not the Atlanta airport. ATL, I forgot what, is that a modeling language?
It's a transformation language for model.
A translation language for model transformations, okay. So I had something in there, sort of modeling. Then they're applying mutation to new problem areas. So this is usually involves a new language or a different, often a modeling language, but model-based testing is a common. And who was that? Was that you, Masa, saying you're looking at mutation for model-based testing? Yeah, so that's, you're not alone. That's good. Security applications, I was surprised there's only one. I expected more of that. So security, there are lots of ways to specify security protocols. One of the most security vulnerabilities now are software problems. Sometimes they're incorrect implementations of a security protocol. Sometimes the protocol itself was flawed. So the idea of mutating a security protocol is to create slight variations of the protocol, and then develop tests for the mutated protocol, and see if the implemented protocol what the implemented protocol will do with those tests. So specifically define security vulnerabilities. And it's a pretty promising approach. One of the problems with mutation is it's incredibly expensive because we just get too many mutants and too many equivalent mutants. Narrowing it down to a small area, like just the security protocols, allows us to reduce most of the expense of mutation because it's a much smaller problem than generally does the program work. Web applications is a common issue in testing in general now, not just mutation. Mobile applications, Okay, so that's I guess both of these papers are my PhD students. So that fits. I found one on detecting memory faults I didn't read in software. I didn't read the paper. I'm not sure if that was hardware or software, or maybe a combination of both. I should have mentioned way back in the 70s when mutation was first conceptualized, it came from a hardware background. There's an idea called stuck-at fault in chips where a resistor gets stuck in a particular state. And so that's a way to test electronic circuits. And it's been around for quite a while. And it's a kind of, they mutate the hardware circuit in a sense by forcing a switch to stay in a certain state. And that was the initial idea for software mutation. And there's a whole stream of mutation that's been sort of came around back into the hardware world, where they mutate things like the specifications of the hardware and the hardware itself. And I don't understand any of that. I've just seen it. So anyway, mutation for memory faults for graphical user interfaces. Why is that on there twice? I guess it's important, yes. Somebody mutated my slide while it wasn't like that yesterday, I just want to say. So these are a number of the problems that have been published about in the past few years. And I want to start, this is one of the biggies. So mutation has been around for quite a while. The first paper was 75, I think. Dick Lipton came up with the idea, and Lipton, DeMillo, and Sayward published the first paper. Actually, Lipton supposedly invented it in a graduate class he took with Dave Parnas, and Dave Parnas gave him a B and said, "This is a horrible idea." How many people know the name Dave Parnas? If you're in software engineering, you should know the name Dave Parnas. Has anybody ever heard of object-oriented programming? He essentially invented object-oriented programming. He invented the idea of data abstraction. So have you all taken a data structures class? Yeah, he invented data abstraction, which led to object-oriented programming. So maybe the granddaddy of OOP. Tomlinson invented email. Really? That was invented. Somebody invented the mouse. That was designed for hypertext, to work hypertext back in the 40s, I think. Yeah, it was, I mean, he came up with that idea. There's a paper on the process for decomposing modules into components or something. And it was, don't focus on the function, the algorithm, focus on the data. Here's an example where everybody think industry invented JUnit. The idea of test frameworks has been around since the early 80s at least. I saw a PhD thesis. I was a student, so it was like 83, 84, that talked about developing a test framework. But then it was invented and JUnit was implemented. And it was better than all these things that PhD students created. It was easier to use, it was simple, had all this support software. But people think that came from industry. It didn't. The same with the web. All the ideas were published in research papers leading up to that. But then, yeah, we do get ideas from industry, and maybe we take the idea and then we publish it. I mean, I don't know if that happens explicitly, but it's quite likely that, oh, I see this, let's category partition testing. Well, there's a technique called category partition testing, which is really the basis for all the input space partitioning ideas. What's his name? I know him. I'll remember his name probably later. He worked at Siemens Research Lab in New Jersey, and he just went around to a bunch of developers and said, how do you develop tests? And they started telling him. So he put it together, he organized it, categorized it, and they said what they really do is they look at the input space, they categorize the input space, and they have this informal process where they wind up with these sort of tests. And he formalized it and defined a process called a category partition. So this is really openly, copying these people, and it's been a great hit. It's a very widely used technique for developing tests. So it's one of the things I teach in my classes, and it's the most widely used because it's easiest to apply. You don't need automation, basically. You don't need good tool support. So that came directly from what people were doing. I had a project back in the 90s, it's about 5 or 6 years, funded by Rockwell Collins, they wanted help with what they call specification-based testing, taking their specifications, developing tests automatically, and Rockwell Collins develops airplanes and software for avionics, so they needed it to satisfy MC/DC, so that was a big part of it. And I took several visits there talking to how do people do it now, what do they want to do, how do they want it to move. And one of the things I kept finding out is that I was big into formal specifications at the time. I told you I was a math major. I love formal specifications. And I kept talking about pushing more formal specifications, and they had formal specifications, but what I kept finding is that nobody used them. So they told the managers, yeah, we use these for everything, but then they told me in the back room, we don't like that crap. We don't understand it. We write the software. This is how we do things. So I started saying, well, what about UML? I said, oh, well, we love UML state charts. Yeah, sometimes we take our specifications that they tell us we're supposed to use and we write them in state charts. And then they say we need formal specifications. We say, yeah, we did that. It's over here. And they never read it anyway, so it doesn't matter. But they were using state charts. So I actually sort of swung my research into sort of the model-based view. So I wrote a paper on developing tests from state charts, UML state charts. It was the first, it's now called the first model-based testing paper. I didn't invent model-based testing; those guys did at Rockwell Collins. But I wrote the paper with my master's student. It wound up losing me the grant because the people at Rockwell Collins running the money said, well, we wanted this project to be about specifications. Now he's doing this models, UML stuff. That's not specifications. But it was actually useful, right? So yeah, I stole that from industry in that way. And I think that was probably a positive thing. Although I don't remember the people I talked to. But they're essentially, we're not mathematicians. We don't use specifications. And my view is, but you should be mathematicians. And then when I go back to my students at Mason, they're like, math? If I wanted to be math, I'd be a mathematician. I'm an engineer. So yeah, you're right. And there should be more cross-fertilizations. One of the big problems with research and software engineering is we don't connect with industry enough. That's a huge problem. 90% of the research published at ICSE has no chance for ever being adopted by industry. Zero chance. So obviously we're going to write research papers that don't go anywhere because it's all speculative. It's science fiction. But why should we write fantasy? Fantasy is the rules are changed in the universe. That's what defines a fantasy book. Science fiction book means we have the rules, but maybe we find out something else. We find there's a way to defeat the light speed barrier so we can have faster than light speed travel. We find a way so that we can be put to sleep for 1,000 years and we can travel to other stars. Or we learn how to control gravity so we have that's all science fiction. We should be writing science fiction papers. But writing fantasy papers, that's useless. Why should society pay us to write research papers that have no chance to ever help real programmers develop real software better? Okay. That was Lionel Brion's essay that he stole from me before I said it. Okay, let's talk about, so the big problem with mutation is it's too expensive. So it's still science fiction. We haven't figured out how it can be fully adopted. We have lots of computation solutions, so computation isn't a big problem. These are the big problems, human issues. Too many mutants, a lot of them are redundant. Too many equivalent mutants, I talked about that. This is an undecidable problem in general, but we can get we can make a lot of progress, at least partial solutions. How do we get to test Oracle? What's supposed to happen? These are all real problems researchers are working on that. They're still open. This is another one. Practitioners are just not convinced that it's useful. So we do all this work, we get better tests, so how does that help my bottom line? Well, in a competitive environment it does. In a non-competitive environment, maybe it doesn't. So how do you measure that? And the tools are, Java is not a bad tool, but it's not professional quality. You can't use that at a company. So there's this idea of minimal mutation. So this is sort of typical. If I have 50 lines of code, maybe I'll get 1,000 mutants. Maybe 10% or more will be equivalent. I'll need 15 tests. Something doesn't add up. Why don't I have 15 mutants? Minimal mutant minimal mutation is the goal of trying to have this many mutants and drive this to 0. So every test kills lots of mutants, so there's lots of redundancy. And redundance, you can say, is if a test that kills A is guaranteed to also kill mutant B, the mutant B is redundant. I don't need it. So how do we eliminate these? These are some of the approaches. So selective is I try to reduce the number of operators I use. So instead of 25 mutation operators, I use 4 or 5. That still give me good tests. You can read the literature about that in more detail. I sample the mutants. This only works if we're comparing with non-redundancy. This doesn't work at all if we're looking at minimal mutation, if we're comparing with minimal mutation. Subsumption that says essentially mutant A subsumes mutant B, so I can throw out B. We can analyze those on a case-by-case basis usually, or sometimes in a more generic level. And there's actually Marcelo Delamaro, Paul Amon, and I started this project on minimal mutation where we've defined that there really is a minimal set. The problem is we can only find, at current, we can only find the minimal set if we run all the tests on all the mutants. So it's not very useful. We need that before, right? And we identify all the equivalent mutants by hand. So it's not actually useful right now, but this is what we want. Is there a better way to approximate that? So that's a wide open area of research. And there are a bunch of recent papers on most of these topics. So early research has found that 90 to 99% of the mutants are redundant. That's huge. Redundancy is sometimes good in engineering, but not this kind of redundancy. So how do we directly find equivalent? Well, we've minimal mutants, a static analysis, symbolic execution, which is a dynamic analysis, and maybe there are other techniques. We're still looking for something. So that's a big problem that people are looking at now. Detecting equivalent mutants. So as I said, it's generally undecidable. Algorithms have detected, so compiler optimizations was the first. We found about 15 to 20% of the equivalent mutants. This was something I started as a PhD student. We looked for contradictions and constraints like the example I showed you. That got up to around 40% of the equivalent mutants. I think it was Harman and Herons published a paper using program slicing. They found, seems like it was 60 to 70%. I'm sure we can do more. There have been a few papers recently that frankly haven't been very good, and at least a couple of them didn't look at these, so they reinvented some of the old ideas, or they came up with an idea that wasn't as good as the old ideas. Make sure you're at least doing better than what used to be there. As you know, that's advice as a professor to his students. Make sure you look at what's been done before and do better. It's not that hard because we weren't very good. So I think there's a lot of room to detecting. We'll never get 100%, right? It's undecidable. But I think we can do a lot better than what we've done. We've talked about program repair. There are really two big problems there. Finding the fault and correcting the fault. So locating the fault is a completely different issue. Where is the fault in the program? Nobody's found a way to apply mutation to that, but correcting the fault, mutation comes into play because we find the faulty statement or statements, we create a bunch of mutants of those statements. And which mutation operators are best? Are the mutation operators that we currently have good, or should we create new mutation operators? The idea is we have everything automated, so we can create 1,000 guesses and evaluate them all individually and see which ones makes the program correct with respect to the current tests, or at least better. So each correction is called patch, and the patches can be mutants. So there's still a lot of open issues in that. What are the best mutation operators there? So Halmstad talked about current research where some of the tools have thrown away part of the output and said, well, it works now because we don't get the failure. That's not fair. Mutation operators shouldn't do that. So part of the work there is let's create mutation operators that only do things that might actually fix it instead of fake it. Right? So here's the thing about students. You hear the older people. We say, we can't do this. This doesn't work. Don't think, well, they can't do it. So, you might start off thinking your professors are really smart and they know things that you don't know and blah, 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 blah. Well, we probably know a few things you don't know, but we don't think as quickly. We're not as creative. We become Now, over time, you just get less creative and your thinking gets slower. And we think, well, I've never been able to do this, so I can't do this. That's why we need you guys to come in and say, he says he can't do this. That's because he's old and slow. I can do it. Oops, that was probably ugly. You have to remember that you're going to do better than we did. I would not accept my PhD dissertation now from one of my students, but my students all do better. And my advisor said that to me when I was sort of midway through my program, and I remember thinking, I can't be as smart as Richard DeMello. He's the smartest guy I know. He's probably not, but I thought he was at the time. And it wasn't until, I remember the time when I went in and I said, I want to do this, 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 this. And he said, that's not going to work. And he said, well, I said, well, I think it will. He said, no, find a different approach. So I went back and I thought about a different approach for 2 days. I couldn't think of one. I said, I'm going to try it. So I tried it, build the program, and I came back to him a couple weeks later and I said, I think I'm making progress. Look at the data. And he said, that's really good. So what did you come up with? And I said, this is what you told me not to do. And I remember him looking at me and I was thinking, is he going to be mad at me or what? He just looked at me. Okay. 2 years later, he told me that was the time he knew I was going to finish a PhD. When I told him he was wrong, and then I proved it. So you have to do that. You have to prove that we're wrong. Okay, it's easy if I'm your advisor because I'm wrong all the time. It's harder with some people. Okay, so I mentioned let me just finish this, a couple more slides. Higher order mutants, because you're all ready for lunch. That's usually one change. There's a coupling effect that says if we kill complicated mutants, then those tests will kill almost all the simple mutants. That's been experimentally verified. But then a crazy guy named Mark Harmon has found that we can actually do some interesting things with mutation, with higher order mutation operators. So that's a kind of an open field. Somebody's used it to try to detect equivalent mutants, to test for some specific properties, probably a lot of other things. You have to be careful because obviously the number of mutants go up exponentially, right? If we combine all combinations of 2, 3, 4, 5, whatever. But there are some interesting things that you can do with those kinds of mutants. So that's an open research area. So I wanted to close by just asking you guys to talk some more. I know we're into the lunchtime, so we should probably talk about this at lunch. How's that sound?